Okay, let's say we have this second order non-homogeneous linear DE. This guy does happen to be linear. A lot of these techniques would work for nonlinear as well. Just the power series would be a little more difficult. We're going to solve this a few different ways. We're going to get an exact solution. Then I'm just going to write up, like, you know how to do this. We solve our complementary solution. We use undetermined coefficients to get our particular solution. I'm just going to write up the actual solution. We're going to use second order Eulers using reduction of order. And we're going to use a power series. And we're going to put all this into Excel and we're going to compare these three solutions. The reason I want to do this is literally the kind of stuff you're doing on project 2. All right, so I'm going to pause. I'm going to type this. I guess you can watch me type this into Wolfram Alpha. So what do we got? Y double prime. Maybe I should have picked numbers. Oh, that'll work out fine. That'll be fine. -3 y prime plus 2y equals 8 plus, oh, I'm going to need to pick some initial conditions here. All right. Let's say, let me make sure I'm recording here. Okay. I need 2 initial conditions because he's second order. Let's say y of 0 equals 2 and y prime of 0 equals 0. Similar conditions to what you might have in your project. Maybe you're doing a skydiver or something, and you get some initial height and an initial velocity of 0. It's 8 plus 4t. And what did I say? Y of 0 equals 2. Y prime of 0 equals 0. I typed that wrong. Okay, so we get an exact solution. Let me make sure I typed him right. 2, 8 plus 4t. Okay, so we get 2t minus 8e to the t. The actual real solution. Y equals 8t minus 2e to the t. I totally lied, didn't I? How are you able to kind of skip through this until it's just written out? 2t minus 8e to the t. 3e to the 2t plus 7. Okay. I'm going to start creating an Excel file. I'm going to put that in there. So first I'm going to build my T column. And I'm going to start at 0. And each one, I'm going to go up by 0.1. So this guy will equal the previous one plus 0.1. And I'm going to go, oh, let's say at least to, let's say 200. One more, because I want that to go to 20. Okay. So 20 seconds, it looks like I'm going there. Then my actual. I want to make sure I type that right. So I'm going to do it from here. So this should equal 2 times, you always need your times in here, my current time, minus 8 times. In order to do e raised to something, you do exp of that thing, of my current time, plus 3 times exp of 2 times my current time, plus 7. And then I can just double click that little dot right there. There's my solution. That thing is growing big. He's getting really big. So when we graph it, we probably won't graph the whole thing. I pick something that grows really quickly. Okay. Now, what will we do for second order Eulers? We're going to say let V be Y prime. So remember, my DE was this, Y double prime minus 3Y prime plus 2Y equals 8 plus 4T. V prime, this here implies that V prime is Y double prime. So if I move everything over here, I'm going to get Y prime equals V and V prime equals, this is V prime right there. That guy is V prime. So I move all this to the other side, 8 plus 4T plus 3Y prime. What is Y prime? V plus 2Y. This is a system of DEs. Y prime equals V. V prime is all this. And remember Euler's method. So in general, F at T n plus 1 is approximately equal to F at the previous guy plus his derivative at the previous guy times delta T. And I know here, by the way, my initial conditions, Y of 0 was 2, and Y prime of 0, which is V of 0, was 0. Okay, so I'm going to put in Euler Y and a second column here for Euler V. I'm going to need these V's. And I know my initial at time 0 was 2. I just made it mad. My initial here was 2. My initial V was 0. Okay, then my next Y value equals the previous Y value plus the derivative at the previous Y value. Y prime is the previous V times delta T. My delta T I used here was 0.1. My next V, this one's going to take a little more typing, but it's right there in front of me. So this next V will equal the last V plus my derivative. I need all this, and that all has to be times delta T. So I'm going to put 0.1 here times all this. I need a times. And then all this will be in parentheses. 8 plus 4 times my previous time plus 3 times my previous V right here plus 2 times my previous Y. And now these two together, because they depend on each other, can scroll down together. Okay, let me pause for a second because I expected my numbers to be a little closer. Let me make sure I typed all that right. Yeah, I knew something had to be a little wrong because the actual and the Eulers should be pretty close for the Y values. And it's right here, when I move that 2Y over, this should be a minus 2Y right here. So to make sure I don't mess this up, I'm going to come back to my sheet and Control Z a couple of times. Okay. So that was here. That should be -2. Okay. Highlight both of those. Got a little better. I'm going to double check it again. Okay. So the issue, everything was right in here. The issue was my delta T was too big. Remember, the smaller the delta T, the better Euler's is going to do. With power series, that doesn't matter. Power series, you can use any delta T you want because all you're doing is plugging in values into a polynomial. So here I have changed my delta T to 0.01. So here I had that. And then I changed my delta T in both of these spots to 0.01. Remade sure everything scrolled down properly. And now we can see, I don't really care about this column. This column isn't doing me any good. I'm not going to graph it unless I wanted T versus V. If this were position velocity, sure, maybe I want to graph velocity. But what I'm really checking here is how close these are. And look, that's a pretty good fit. And that's going to be true all the way down. Like, look, you can see we're diverging a little bit. If I were to graph, I highlight just these three and hit insert over here, scatter plot. Come on, that's a pretty good graph there. It's not perfect. We're starting to diverge a little bit, but especially near the beginning, we got a pretty good approximation. That's what's going to happen with Euler's if you do everything right. Now let's do a power series. This is the main reason why I'm recording this video, because we have a non-homogeneous power series. You're going to have something similar in your project too. So this is going to take a while. All right, power series. I'm going to rewrite the DE here. 3. Well, then what do we got? 8 plus 4t. And my initial conditions, y of 0 equals 2. That's going to be my A0. Or I'm going to use that to get A0. I shouldn't say that yet. That may not end up being my A0. Yeah, that's true. That is what I need. That's A0, and this will be A1. Okay, so we assume that y equals some infinite sum n equals 0 to infinity, a sub n t to the n. And you've watched me do this a couple of times. Y prime then sum n equals 0 to infinity, a n times t to the n minus 1. And you've watched me do this a bunch, hopefully. First term 0, so we might as well start counting at 1. And then I need this to start at 0. I need this to be t to the n. I'm going to drop this down by 1 and simultaneously raise all those up by 1. That's y prime. Then y double prime. Just taking the derivative here again, we get n equals 0 to infinity, a n times n minus 1, t to the n minus 2. And again, we're going to play the same game. First two terms are 0. So the 0 and 1 terms, I might as well start counting at 2. And then I need this to be t to the n, and I need this to be 0. So we're going to drop this down by 2 and raise all those up by 2. Okay, there's my y double prime. Okay, now we're going to squish all this together in our dE. So I am going to have, I'm going to need a lot of space here. It was y double prime minus 3y prime plus 2y equals 8 plus 2t, 8 plus 4t. But wasn't it 2t? Oh, I guess in the answer I had a 2t. Okay. We'll deal with this in a minute. Okay, so what do we get here? Sum n equals 0 to infinity, an plus 2, n plus 2, n plus 1, t to the n, minus 3. And here we had n equals 0 to infinity, an plus 1 times n plus 1, t to the n, plus twice the original. That was just n equals 0 to infinity, an t to the n. And that's supposed to equal not 0, this stuff. Okay, we have the same starting point on all three of these, and they're all t to the n. We can squish that together into one single sum. That's all times t to the n, and that's supposed to equal this over here, 8 plus 4t. Okay, and then what we usually do when we have a homogeneous dE, we have a 0 over here. The only way an infinite polynomial can be 0 is if every coefficient is 0. So we set this whole thing equal to 0. That's not what we have here. Remember, this is just a bunch of stuff. This is like 7 plus 3t plus 9t squared plus 85t to the third. This is an infinite polynomial. And over here, what we usually have is 0 plus 0t plus 0t squared, 0t cubed. We usually have all zeros, so we just equate like coefficients. It's the same idea here, but they're not all 0 on the other side. What we're going to have is some first term over here must equal the first term over here. The t to the first term must equal the t to the first term, and so forth. So we want to think of this right side. So the right-hand side is 8t to the 0 plus 4t to the first plus, and now all the rest will be 0. So we have to do the first couple by hand, then we get a recursive formula. Okay, so I'm going to start plugging in n equals 0 here into this left-hand side for all my n's, and that will give me my t to the 0 term. So that would be what? A2, 0 plus 2, times 2, 0 plus 1, 1, minus 3, A. There are not going to be any 9s anywhere here. These are all A's. I'm plugging in 0 for all the n's. 1, 1, plus 2A0. That's all times here. I'll be explicit here. This is all times t to the 0. I'm plugging in 0 for all the n's. And that's supposed to equal 8t to the 0. I know A0. He's 2. That was one of my given conditions. I know A1. He's 0. I can solve for A2. So what do I get here? I get 2A2. I don't think you need to watch me write that. Minus 0 plus 4 equals 8. So I've just simplified all this. I know A1. How do I know that? Because those were my initial conditions. A0 is always y of 0. A1 is always y prime of 0. Those were given. So, like, I think we just get A2 equals 2 here, right? Okay, let's find plug in n equals 1. So I'm going to go back up here, plug in n equals 1. What do I get? A3 times 3 times 2, plugging in 1, minus 3A2. It's a good thing I just found A2 times 2 plus 2A1. Hey, it's a good thing I know that. And this is all times. You don't have to write this. I'm showing you this explicitly. That's times t to the n. What's in? 1. T to the first is supposed to equal 4 t to the first. So that means this stuff here has to equal 4. So what do we get? We get 6A3 minus 6A2 plus 2A1, he was 0, must equal 4. I know A2 because I just found him. So that's 6A3 minus, what do we get there? 12 equals 4. So 6A3 equals 16. A3 will be 16 over 6 or 8 over 3. You guys will definitely have to go through and check all of my details here and make sure all the details are correct. But let's assume I got that right. Okay, now let's plug in n equals 2. And to make my life easier, I'm going to recopy this down here. Oh, so I'll do it down here. N equals 2. Now, all the rest of my terms over here, I don't have a t squared. I don't have a t cubed. I don't have a, all the rest of them are going to equal 0. Not the coefficients, what I set all this junk equal to will equal 0. So I plug in n equals 2. What do I get? A4 times 4 times 3 minus 3. A3 times 3 plus 2A2. Again, t squared equals 0 t squared. So this just equals 0. All right, so what do we get here? 12a to the 4th minus 9. Oh, we did end up with a 9 on the page somewhere. I got to make sure that 9 looks different than my a's. Plus 2a2 equals 0. All right, what did we get for a2? 2 and 8/3. So that's 12a4 minus 9 times 8/3. I literally just forgot. I think we got 2. Yeah, A2 is 2. Okay. So 12A4. Let's see, that's 72. I might need to get my calculator out here. Let's just use Wolfram. So that was 4 minus 9 times 8 over 3. I think I wrote that right. 4 minus 9 times 8 over 3. Oh, yeah. I guess we get some cancellation there, huh? So that's just 4 minus 12. We get negative 20 there. Okay, that's convenient. So we're not getting nasty fractions equals 0. So A4 will be 20 over 12. Let's reduce that. 5/3. 4 goes into both. Yeah, I think we get 5/3. Okay, now you would want to keep going. You're not done. You would want to get at least up to A10. At least. The more terms you keep, the better your power series is going to be. Okay, so I'm just going to stop here just for illustrative purposes. So my power series, remember, it's just a polynomial. It's going to be y equals a naught plus a1 t plus a2 t squared plus dot, dot, dot. Okay, so what do we get here? I'm going to get 2 plus 0 t plus 2t squared plus, I think we got 8/3 for T3, A3. Remember, the A goes with his own power. A3 goes with T3. And then 5/3 T to the fourth. I'm going to stop there, but you want a lot more than that. Okay, now let's put that in our Excel spreadsheet. Okay, so let's call this the power series. So I know my initial amount was 0. And now this one's supposed to equal, I could have just typed it here. We'll just type it from the beginning because we're going to get 0. Oh, sorry, that wasn't even true. My initial amount was 2, but we're going to get that. So I don't have to put that in. That's what we're going to get. So this should equal, and I'm literally just going to type in this polynomial. 2 plus, I don't need the 0t. I'm not going to type that. 2 times current t squared plus 8/3 times current t cubed. It's not previous like with Euler's, it's current plus 5/3 times current t to the fourth. And you would just type out some big, long, nasty thing, go at least up to the 10th power, at least. What went wrong? There's no t. Okay. Oh, good. That worked out. Okay. Double click on that, scroll it down. If you've done everything right and you've kept enough terms, for the first few entries, these should be identical. Like, look at that. I only kept 5 terms. I went up to t to the fourth, and this is working perfectly at first. It's not exactly equal to the actual. Those are, in the real world, these are not actually exactly the same, but up to the number of decimal places Excel shows you by default, it's actually, in its mind, it has more decimals than what it's showing us. But what it's showing us, these should match perfectly. If they don't, you've done goof somewhere. That's at first. Notice that the power series is a better approximation than Euler's. So what you're going to write in your paper, like maybe we'll just graph. I'm going to hide this column. And I'm going to graph these 3, but I'm only going to graph the beginning, maybe up to where that power series starts to diverge off. Oh, he's still looking good all through here. Once I get over 1, I bet it's going to, yeah, like now look, it's terrible. So maybe up to 1.5. Let's do that. So I'm just going to highlight that. Insert graph. Of course, I would want to label the graph, label my X and Y's, and put a title on it. In your actual write-up, you're going to have a bunch of different graphs. Graph actual versus Euler, actual versus power series, so forth, both near your starting point and far away from your starting point. And then I would write up, let's find an actual error. It would everything's an absolute value here. I don't care about who's bigger or smaller, but maybe I would do this minus that and say, look, after 0.02 seconds, the error in the Euler is pretty big, whereas the error in the power series is zero up to what Excel is showing me. I think if I open these up, it will show me more decimals. So we can see, yeah, there is a little bit of a difference, but it's very small. So the power series solution is a much better approximation at first. But then by the time I get down to, what did I say, 1.5, now the power series is a not very good approximation. Look, it's way down here. Euler's is still not perfect, but it's much better. So near the start, power series is better. Further away, Euler's will be better. And if we go far enough, see, I didn't keep that many terms. If I'd kept more terms, one of these is going to shoot off to infinity. What's probably going to happen is your power series. Where's my other graph? I lost my other graph. I don't know what happened to my other graph. There it is. It's way down here. This is not cooperating. What's going to happen is your power series is going to diverge off infinitely. Once we get really far away, it's going to be a terrible approximation. So don't just give me one graph. Like sometimes a group will want to do this. They'll just highlight all these, the whole thing that they've plotted, insert. Okay, let me go really far to show how these might diverge because my numbers aren't getting very big here. I just want to show you what can go wrong. I'm going to delete these graphs. By the way, once you get a graph you like, just Control C on it, go over to your paper you're typing up, your Word doc, whatever. Control V, boom, you've got it copied and pasted. Put all your titles on and all that first. Okay, I'm going to scroll all of this down further until we get like gigantic numbers here. And I want to show you some of the ugly graphs people turn in sometimes that are not enough. You need more than this. Okay. Yeah, maybe that. Maybe that'll be enough to illustrate what I'm trying to illustrate here. So I'm going to highlight all those, insert. Like this got so big, I can't see any of the fine detail here. It looks like my power series is all at zero. It's really not. It's not all at zero. It's just so much smaller than these that I'm losing all the fine detail. So it'd be okay to include this graph. I'm saying not saying don't include it. I'm saying this can't be your only graph. You need a graph that's zoomed in near the start where we can really see where they're all close together. And then maybe have another graph that's far out and shows everything and shows this divergence here. Okay, so this is literally what pretty much every group is going to be doing. Exactly this kind of stuff. So there's a little trickiness here with this non-homogeneous power series. Your Eulers might be a little different. If you have a first order DE, you're not going to have to play this reduction of order game. You're just going to do regular Eulers. Okay, I think that's a good place to stop.